This is AQA A-level chemistry topic. It's from year 13 and we're looking at acids, bases and buffers. This is part 6 of this topic, and in this video we are going to focus on buffers. So listen carefully, have a go, see how you do on the activities, and then you get to see how confident you can be going into the exam with what you know. So, buffers, we need to know what a buffer is, how they work, and then we've got calculations that we associate with them. So there's quite a lot to take on board. We've got the definition here. A buffer is a solution that can resist changes of pH when small amounts of acid or base are added to them. And that's a really important component of the definition, because if you add huge amounts of H plus or OH minus, the pH is going to change. But on small amounts, it will resist those changes. So predominantly we focus on acidic buffers. That's what the calculations will be based on. And we've just got a few questions here to guide you through what an acidic buffer is and how it works. So the first thing to take on is that an acidic buffer is made from a weak acid and a salt made from that acid, but using a strong base. So what might you use? Well, one of the most common ones is ethanoic acid as the weak acid. And if I were to take ethanoic acid and react it with a strong base, the strong base that I have in mind is sodium hydroxide, then the salt that I'm going to make from that is going to be sodium ethanoate. So I would take ethanoic acid and sodium ethanoate, and putting those together would be my buffer. Now, what do we think the pH of an acidic buffer would be? Well, the clue is in the name. It's acidic, but also it contains ethanoic acid and it contains a salt, which is neutral. So we would expect the pH to be an acidic pH. We would expect it to be below 7. Now, we're going to work through how we can use buffers and how we can do calculations. So start off by thinking about the questions that are on here. So we're working with the acid HA. We want to write an equation for the dissociation of it. Well, that means that we're breaking down the HA into its H plus and A minus, and it is a reversible reaction, as all of these always are. You're then asked for the expression for Ka. Well, once again, we remember from Kc, from Kp, that we have products on the top and reactants on the bottom. So I've got my H plus times A minus over HA. And it's all concentrations in square brackets. In terms of the equilibrium lies very far to the left. Weak acids only partially dissociate, remember. They don't dissociate much at all. So very little of the acid in a weak acid dissociates. So let's move on with a few more questions. Now let's forget about the acid component of the buffer, and now let's think about what happens with the salt component. So the equation, I've got my NaA, aqueous, breaking down into Na plus ions, aqueous, and aqueous A minus ions. And what do we know about the dissociation of NaA in solution? Well, actually, this is a much more general question. This is a what do we know about salts in solution? And salts will fully dissociate in solution. So we've got two parts here that we need to think about. We've got an acid that only very slightly dissociates, and we have got a salt that we know fully dissociates. So we make some assumptions and we accept some of that key information as well. Because the weak acids are only very slightly dissociating and the salt will dissociate fully, we actually assume that all of the A minus ions that we have are coming from the salt and none from the acid. In really simple terms, we assume the weak acid is not dissociating at all, and we know that the salt fully dissociates. So now, as it says here, look back at the information already gathered. We know the purpose of the buffer is to resist changes in pH. A buffer solution is a mixture of HA and A minus. So if I had my mixture of HA and A minus, what would happen if I added a small amount of H plus? Well, take my H plus. Am I going to react it with the HA or the A minus? Well, logically, I'm hoping that you're thinking it's going to go with the A minus. So my HA concentration is actually increasing there, and my A minus concentration is decreasing. Similarly, if we think about the next question, so I've got OH minus, and I've got to decide, is that going to react, being a base, with the HA, the acid, or the A minus, the salt? And it's going to react with the acid. This is essentially a neutralization reaction. It will accept a proton, making H2O, and we will be left with A minus. So in this case, the A minus concentration goes up, and the HA concentration goes down. So I'm going to run through some of the key principles here, just so we can start to build towards the calculation. So here's my expression. Ka is H plus times A minus over HA. Let's rearrange that to make H plus the subject. So that means it's Ka times concentration of HA over concentration of A minus. But actually, we know that Ka is a constant. It's the acid dissociation constant. So there's actually a proportionality here. The H plus concentration is proportional to the concentration of HA over the concentration of A minus. And we've just been speaking about what will happen if I add small amounts of H plus. I will make more HA, and there'll be less A minus. If I add OH minus, there'll be less HA and more A minus. But actually, for a buffer to work, the buffer needs to contain a large amount of HA and A minus, because what that then means is when we add the H plus, the numbers will only go up or down very slightly. So there will be very little change in H plus concentration. So HA, that's, remember, from the undissociated weak acid, and the A minus, which is from the fully dissociated salt. We are assuming, remember, that none of the HA has dissociated. So if H plus is added, the HA concentration increases, the A minus concentration decreases. But we're adding a small amount of H plus to a very large amount of HA and A minus, so the overall change will be tiny. If I add OH minus, the A minus increases and the HA decreases, but again in very small amounts. So the overall concentration of H plus only changes marginally. And we're taking us back to that ratio there. So let's have a think about basic buffers. What could you say about this based on what we've seen? Well, ammonia is acting as the weak base, and ammonium chloride is the salt that we've made from ammonia, and a strong acid, in this case that would be HCl. If I add H plus, then that's going to react with the NH3 with the weak base to make NH4 plus ions. So my NH4 plus concentration goes up and my Cl minus concentration goes up. My NH3 concentration goes down. And if I add OH minus, that will react with the NH4 plus to make H2O and NH3. And remember, if H plus concentration is equal to Ka times concentration of HA over concentration of A minus, where Ka is constant, then the H plus change is really determined by the ratio of concentrations of HA and A minus. So let's put this into practice with a couple of calculations. Oh, in fact, no, sorry, we're doing uses of buffers. So what uses of buffers do we know? And I've said here it can be natural or synthetic. Well, one of the key ones is HCO3 minus ions, and that is a buffer within the blood, and that's to keep the pH of blood between 7.35 and 7.45. So we've got an equation here for what's happening. Carbon dioxide and water react to make H plus and HCO3 minus in a reversible reaction. But the carbon dioxide, we also need to know where it comes from. It comes from respiration. The H2O is present in blood. If we don't regulate the H plus concentration, the blood pH can actually drop, and there can be a disease called acidosis. It can cause the body to start to malfunction. It can cause somebody to go into a coma, ultimately. But we have a buffer here. If the H plus is increased by an addition of a small amount of H plus, the equilibrium will shift to the left to reduce it. And if the H plus is decreased, the equilibrium will shift to the right to increase it again. So let's take a look at a couple of buffer calculations. We've got a relatively straightforward one to start. So let's start with the expression for Ka, H plus times A minus over HA. And we're interested in H plus, so we've rearranged to make it Ka times HA over A minus. I've got all of the figures for this. I've got my Ka value provided, I've got my concentration of ethanoic acid provided, and my concentration of sodium ethanoate provided. So I've put all of those in. Now actually, you can probably do this without a calculator because you're multiplying and then dividing by 0.2. So we have an H plus value of 1.7 by 10 to the minus 5. I can now substitute that into my pH expression, and I get negative log to the base 10 of 1.7 by 10 to the minus 5, which gives me a pH of 4.77. A considerably more complicated question here now. See what you can do with it. I think the important thing to say on a question like this is, if you do get stuck and you're not sure where you're going to go with it and you're a little bit overwhelmed, look at what you can work out. For example, you have been given a concentration and a volume of NaOH. It's always worth working out the number of moles. It's probably going to be worth a mark. So I've color-coded so we can see 500 cm cubed, 0.2. Remember to convert your volume into decimeters cubed, and we end up with 0.1 moles of NaOH. Let's do the same for HA, which I've also been provided with information for. So my volume, 250 cm cubed, my concentration is 1. Convert my volume into dm cubed, I get 1 times 0.25, that's 0.25 moles of HA. Now, what we then have to do is work out the number of moles of A minus, which is equal to the number of moles of NaA that we've made that we know fully dissociates. I can see the acid is in excess, and it would always have to be in a buffer calculation like this. But the NaOH I had 0.1 moles of. That means I'm going to make 0.1 moles of NaA, and that means when all of them dissociate, I've got 0.1 moles of A minus. In terms of the moles of HA, well, I started with 0.25, but if I've made 0.1 moles of NaA, then on a 1-to-1 mole ratio that we have in this reaction, I've used 0.1 of the acid, which means I've got 0.15 moles left. Now we want to work out concentration of H+, and that means actually we are going to need concentrations, and these are number of moles, so there's still more to do. My concentration of A minus is my 0.1 moles, you can see there, but I'm dividing by 0.75. I've added information up at the top here. This is now the new volume, because I had 500 cm cubed of NaOH and 250 cm cubed of HA. So I've got my new concentration. That is now 0.133 mol dm to the minus 3. I need to do the same with the HA, which is 0.15 that we worked out a moment ago as the number of moles, again divided by the total volume it's now in, which is 0.75 decimeters cubed. So finally, I've got my HA concentration, my A minus concentration, and I've been provided with my Ka. So I can say that H plus is equal to Ka times HA over A minus. I can substitute the figures in. The two that we've just calculated, my 0.2 molar, my 0.133 molar, and my Ka value provided in the question. That takes me to an H plus concentration of 9.4 by 10 to the minus 3 mol dm to the minus 3. And now I've got my H plus, I can substitute that into my pH expression, giving me a pH of 2.02. Now, once you've done this with buffers, I really do recommend seeking out buffer calculations, because actually there can be some that take it even further. There are buffer calculations where you start with a buffer and the question will ask for the change in pH when a small amount of H plus or OH minus have been added. So this video was very much introduced the concept of these calculations, but actually building on that and carrying them out and seeing how you do is at the heart of being successful on this topic. So that takes us to the end of this video, and it takes us to the end of the acids, bases and buffers topic. Thank you for listening, and goodbye.